Hello and welcome to this Elasticon presentation, Simplify Log Pipelines with Kubernetes and Searchable Snapshots. I'm Joshua Robinson from Pure Storage, and I'm going to talk today about a common problem that our customers are solving, trying to build these log pipelines at more and more scale. Simply put, the goal that we keep seeing from numerous customers is desire to have agility, being able to deploy lots of log pipelines, Elasticsearch for different use cases, different environments, be able to scale up and down, spin up, spin down clusters. And they want to be able to have that agility by removing operational complexity. So remove a lot of the day-to-day challenges of maintaining, scaling, upgrading, and just keeping these clusters running well. How to do that? Well, I'll talk in the presentation today about two key things that tie into new features from both Elastic and Confluent, the companies behind Kafka and Elasticsearch, that are really interesting features that improve the ability to automate and disaggregate these applications. The problem that we all face is the ability to build pipelines to extract data. Numerous data sets and numerous different teams who need a different set of applications, different configurations, different parameters, different styles in order to extract value. It could be the same data sets. One team is trying to debug application performance issues. One team is working on click-through prediction. Another team is working on security and trying to build a system that can help them troubleshoot and debug when there's a security incident. And what we consistently see is a really key metric to being able to be successful at a data project is how long it takes to build that next data pipeline, how long it takes to deploy, tune, configure, get it right, and get it to actually extract the value that you're trying to extract from your data. And that is a nice metric because it encompasses so many more things than just performance. It encompasses your environment, your infrastructure, orchestration tools, scripting, monitoring. All of these things come into play. And it's that N+1, that next pipeline, and how long it takes that really gives you a good sense of how successful your project will be. And just to make this more important, there's critical needs in addition to just deploying a production Elasticsearch cluster. There's a need to do test dev workflows, to test your downstream applications to make sure that they continue to work correctly with real data that may be sitting in your Elasticsearch instance, as well as the desire to iterate, maybe deploy new software, new features, change the schema, the structure of your data. And all of these contribute to needing more agile, more speed in deploying, changing, and tearing down Kafka and Elasticsearch clusters. So I mentioned before two key ideas, automation and disaggregation. The first one is straightforward, I think. Today, a lot of our customers struggle with manual processes to provision servers, select the right CPUs in memory, provision storage, connect all the applications, get them installed, choose the versions. All of this ends up being a large number of manual processes, clicks, or a ticket that you have to submit, and takes days or potentially weeks to actually hear back and have that environment fully provisioned because of the manual nature of these processes. And so while it's easy and straightforward to say the solution is automation, what's not so straightforward is, wow, how can we actually reliably and scalably automate? We'll talk about that, of course, later. And the second key way that we can simplify these environments is disaggregation. And what that means is independently scaling, operating, and managing your applications in your compute and your storage and data. When you scale them independently, you operate them independently, what you're effectively doing is moving from a direct attached storage or a converged architecture to a disaggregated architecture. This converged direct attached storage architecture is originally pioneered, designed by HDFS about 17 years ago, now based on constraints in the data center about 17 years ago. Slow networks, spinning disks that were unreliable, and a lot of things have changed now. Networks are significantly faster, flash storage is becoming more and more pervasive, so that the advantages of a converged architecture are not nearly as important as they were so long ago. Disaggregated approach, or a much more cloud native architecture, operates your application and your servers independently of your storage system. And this has a lot of benefits. On the cloud, it can be your EC2 instances and your S3 or EBS. On-prem, it can be something like the pure FlashBlade, which you see here, which incidentally is one of the products that we build. Disaggregating means that you have the ability to independently scale these resources. First of all, you have desire to increase your compute because you need to ingest more complex documents, or you need better performance time on your queries. You can add more compute without having to add more storage. And of course, vice versa, if you need to increase the retention, say double the time that you need to store your documents from 1 year to 2 years, instead of needing to add a set of more data nodes, you can simply add more storage and have a seamless scaling experience from the storage perspective. So it allows you faster ability to scale, but also more efficient resource usage because you're only adding those resources that you actually need. Of course, a second and very important benefit of that disaggregated approach is improving your recovery times from node failures. So in a traditional converged direct attached storage approach, because each node is actually both your compute resource and your storage, when a node fails, you need to recover your protection level by rebalancing data. So you need to recover those primary or secondary replica shards that you were lost on that data node by copying data over from the remaining nodes and rebuilding those shards elsewhere. This is a time-intensive process. Data has to go over the network, be written onto your storage, and importantly, it's proportional to the amount of storage you have used in your cluster. So if your cluster doubles in size, your node recovery time also doubles in time. In a disaggregated approach, if a compute node were to fail, you can simply recreate that node on a different physical location and have it reattached to the same storage, whether that's a remote drive of some sort or connecting to a software-defined storage like Portworx. On the storage side, you can delegate these failure handlings to the storage. So for example, FlashBlade, which you see in the diagram here, if one or two of these blades were to fail during operation, all of the node failure handling happens internal to the system, completely transparent to the applications. So it greatly simplifies node failure recoveries. And that has a knock-on effect of things like software upgrades. It makes them simpler as well. So traditional approach, because an upgrade is one of the more high-risk times for your software, there's a good chance, relatively good chance, that your node is rebooted for an upgrade. It might not come back. And so traditional approaches often advise for doing a rebalance operation before each node is upgraded. Of course, this takes proportionally longer if those rebalances also take longer. In a disaggregated architecture, your nodes, your data nodes, your brokers are either stateless or nearly stateless. And so you can upgrade them much faster, one at a time, and only taking the time it needs to do a reboot and restart of the software. As if one of those nodes were to fail along the process, you haven't lost any data. The data is all still protected by your storage, and you can recreate that node logically elsewhere. So all these disaggregated benefits help make your data nodes and your brokers more lightweight, easier to manage, and makes failure recovery easier. So disaggregation helps take a lot of the burden from operational challenges. So I've talked abstractly about these benefits. I want to talk briefly about a real life example of one of our customers who's using the combination of Kafka and Elasticsearch along with Prometheus. And Kafka and Elasticsearch is a very common pairing that we see with our customers, hence the focus on those two applications. And what they're doing is using Kafka Elasticsearch in Kubernetes on a FlashBlade to monitor their large 7,000 node compute farm. So they have a variety of applications running on this compute farm, and they're collecting logs from these applications for different purposes. The basic, inevitable, my application isn't working as expected. It's a distributed application. It's really hard to debug unless I have all the logs in a central location. But the reason specifically they chose this particular architecture, bringing together Kubernetes, these applications, and the FlashBlade in a disaggregated environment, is because they have occasional audit events where they need to audit from external auditors all these different applications on their compute farm. So what they do during these audits is dramatically scale up the resources for Kafka and particularly Elasticsearch so that the audit can happen quickly, queries return quickly, all the data is available, fully indexed, and then they scale back down for day-to-day operations. And we're using this environment, which I'll talk about in a little bit more detail later. These scaling operations up and down take minutes of time, and then all of the actual work is automated behind the scenes. And this is a really great benefit for them, just to keep their environment simple, so they don't have to think about infrastructure and can think about and worry about the applications and actual use cases of the data. So to explain in more detail these key new features from both Confluent and Elastic, I'm going to use this logical log analytics pipeline, logs flowing from a log source. In the case of the demo pipeline that I have in my Helm chart, a synthetic log generator going to Confluent Kafka, beats pulling that data from Kafka, applying some lightweight transformations, in my case, JSON parsing, and indexing that in Elasticsearch. So a straightforward log pipeline, and all of the benefits of automation and disaggregation happen behind the scenes, so don't impact the end user experience of how you would ingest log data and how you would use Elasticsearch and Kibana to search through it and make that data accessible. And on the bottom of this diagram, I've shown the two key storage pieces from Pure, Portworx and the FlashBlade, which is the white bezel on the right. And I'll talk more about how automation and disaggregation combine new features in these applications at the top with the storage. Because that's really, I think, the interesting part here is how these work together to make operating all of this at scale much easier. So first is automating these environments with the Kubernetes operators from Confluent and Elastic. So Confluent has Confluent for Kubernetes, which they've recently released a new version of their operator, which is a significant improvement and streamlined in how you use this operator to deploy various Confluent components. And of course, Elastic Cloud on Kubernetes, ECK, which Elastic makes very easy to deploy different components in the Elastic stack. These two operators are basically building on top of automation fundamentals principle inside of Kubernetes, but with application awareness. As end result for your user is you can specify, I want a Kafka cluster with this many brokers and this type of storage, and I want an Elastic cluster with this many data nodes and this type of storage and these size of volumes. So these operators coordinate the deployment of these clusters, but also maintaining them so that if things fail, they can be self-healed, and coordinating upgrades or scaling operations. One of the things I particularly like with Elastic ECK is if I need to add a node to scale my cluster, it takes me seconds to edit a YAML file, hit apply, and ECK will coordinate the scaling up or down of that cluster. Now, there's a lot of automation that goes on behind the scenes, and that connects to Portworx, which is Pure's Kubernetes native storage layer, which provides different storage classes as needed for these applications. And coordinates when, for example, Kubernetes and the operator migrate one of the pods to a different physical node and reattach that storage. That's all coordinated together behind the scenes with the operators, Kubernetes, and Portworx. The end result is automation so that these can be deployed in minutes instead of hours, days, or weeks. The second really interesting and key feature from both Confluent and Elastic that enables simplicity in these environments is being able to disaggregate with object storage. With Confluent, the feature is called tiered storage. With Elastic, it's searchable snapshots that back a frozen tier. And both of these features operate in effectively the same way. They leverage a remote object store for storing the bulk of your data. Data still lands on a hot tier as per usual, but then can be moved quickly to an object store so you can store terabytes, hundreds of terabytes, petabytes of data in a single cluster without having to scale up your node counts dramatically. Both of these features are part of the premium releases, so they're not part of the open source distributions, but they are greatly leverage an object store. So if you were deploying this in the cloud, you'd use Portworx plus whichever cloud provider's object store. If you're deploying this in an on-premise environment, again, Portworx, and in that case, a FlashBlade, which presents an object storage interface. So I'm going to briefly walk through some YAML examples just to illustrate exactly what it takes to deploy all of these features together. I think you'll find that it is not nearly as complex as it may sound. These are all straightforward and easy to configure. As part of the Helm chart, you can see the whole context, but I'll quickly walk through just the key pieces in the next few slides. First, the Confluent operator for Kubernetes. You can see here some YAML. The key things to focus on are in orange, where you specify the capacity that you want for each of your local storage volumes and the storage class. And with Portworx, you can define your storage classes so that you have backed by spinning disk if you want, or backed by local flash or NVMe. So for example, for Elasticsearch hot tier, you'd want to probably back that by NVMe flash storage, but you might not want that for Kafka. And then on the bottom of this, you see the configuration for the tiered storage, where you simply need to provide an IP address for the object storage endpoint, a bucket, and then your access keys so that the Confluent has permissions to read and write from that object store. And this is what it takes to deploy both the broker local storage and tiered storage. For ECK, you have a similar process, installing an S3 repository for a snapshot repository, providing your access keys, and configuring nodes that are part of that data frozen tier. Here, I've configured nodes to be part of hot and frozen. The Elastic recommendation is to have separate nodes as well, but for convenience, they're all here. And similarly, for Elasticsearch, you can specify a volume claim template, specify size and storage class for your Elastic data nodes. Then finally, deploying that frozen tier in searchable snapshots is really a simple two-step process. First, define a snapshot repository, which is the JSON configuration on the left. Type S3, give it your bucket name, your endpoint. If you have a performant object store, I suggest increasing your restore bytes per second so you can actually search quickly against that. And then in your index lifecycle management policy, you have a frozen tier that simply references that snapshot repository. And all of the data movement orchestration is automated by Elasticsearch. That's all it takes to configure frozen tier and backed by searchable snapshots. So finally, I want to quickly present some measurement results just to illustrate the extent of operational benefits you get from using these automation and disaggregated features. First, by disaggregation, you no longer need to do as many rebalances on your nodes. This has some pretty big impacts on things like software upgrade times. So this is a graph comparing a traditional rolling rebalance strategy, which highlights the speed of a rebalance operation with a disaggregated architecture where you don't need to do a rebalance. Of course, the rebalances are much longer and so make the software upgrade much slower. But the key thing here is it increases linearly as your cluster grows, whereas with a disaggregated architecture, your rebalances are constant time. So limited by the amount of hot data on your nodes. But if you grow your frozen tier by 3x, your rebalances will not take any longer, which means you get to grow your cluster without growing the complexity. But of course, if you're moving your data to a frozen tier, you still may want that data to be accessible. Most of our customers aren't using Elasticsearch for archive. They're using it because they may need access to that data in the future, and they may need with performance, not taking days before they get results back. So a quick query test on a 4.5 terabyte data set, and you see that the FlashBlade returned queries 3 times faster than a traditional object store, the AWS S3. So this is important if you want your data to continue to be accessible. You can still query with performance that data. And then finally, the importance of common infrastructure, which means running both these applications, multiple clusters on a single set of infrastructure, single set of Kubernetes nodes and a single storage infrastructure. It means that you can much more easily deploy these environments without having to build bespoke infrastructure silos for each application. So this is a Grafana dashboard of a mixed Elastic, Kafka, ingest workload plus some queries going on, all being handled by the same FlashBlade, taking advantage of the fact that a Flash-based storage system has a much more versatile and flexible performance profile than traditional spinning disks. So in summary, there are 2 key features to automate and disaggregate log analytics environments at scale: the Kubernetes Operators, CFK and ECK, to automate, and that's powered by Portworx, cloud native, Kubernetes native storage. And the second, disaggregating these environments so you can independently scale and operate storage and compute. And those features are tiered storage and searchable snapshots, both backed by FlashBlade's object store if you're in an on-prem environment, of course, your cloud provider if you're in their object store. And together, these make operating and scaling log analytics pipelines much easier by getting rid of all of the infrastructure, not all of, but most of the infrastructure challenges. So for more information, please see the GitHub repository for details on examples of how to configure all of this and the various searchable snapshots, tiered storage, FlashBlade, and Portworx. Google searches can easily find more information on all of those. Thank you for your time, and I appreciate the interest.